Alright, we're looking at some calculations here with a real battery versus an ideal battery. So our battery will be here, which encompasses the ideal voltage source, the EMF, and the internal resistance, and it's connected to a load. We're going to change the values here. We're going to make this a 0.2 ohm internal resistance, and we're going to make this a 20 ohm load. Alright, that'll just give us a little bit bigger effect to look at. Okay, first we want to sketch the IV curves of the battery in real and ideal. So an ideal battery, the voltage will always be whatever the EMF voltage is. There's no internal resistance, and we want it to behave like that no matter how much current we draw. In real life, we don't get the same voltage for any old current draw because there is this internal resistance, but in the ideal case we can. So the real case has to agree when there's no current, right? But then as current flows, we get more and more voltage drop across this internal resistance, which means that the voltage, the terminal voltage across the battery, which is what you would get here, gets lower and lower. So as current gets higher and higher, voltage gets lower and lower, and it does so linearly. And the slope here is -1 over the internal resistance, which we usually call little r. Alright, so low current, we're pretty close to ideal. If we start to get high current, then the voltage really sags, which is, this is how batteries work. So you can't ask too much of your battery. Like you couldn't put 8 1.5 volt double A's together and try to start your car, because trying to pull all that current through the battery will really cause that voltage to sag, and you won't be able to maintain that current. So that's one of the things that the car battery has over those other ones. Alright, so calculate the current through the motor both with the battery, with this battery and with an ideal 12-volt battery. We'll do the ideal one first since it's easier. So in the ideal case, we don't have this resistance. All we have is just this one resistor circuit. So it's a pretty easy application of Ohm's law. So we're going to lose 12 volts across that one resistor. So the current will be 12 volts over 20 ohms, which will give us 600 milliamps. So I'm using some unrealistic numbers here. In reality, this current draw is much higher because we have a lower motor resistance. For the real case, where we have this, in the real case, we have two resistances in series here, so we have 20.2 ohms of total resistance, and we want to know how much current is flowing, so we can just use that total voltage drop, which will be 12 volts shared across the internal resistance and the load. So we just do basically the same calculation we did before, except instead of 20 ohms, we have 20.2 ohms, which will give us 594 milliamps. So not much of a change, but again, our numbers aren't super duper realistic, and in reality we have a little higher, or a lot higher current, which will give us a bigger voltage drop across the internal resistance. But it illustrates the concept we're going after. Okay, finding the terminal voltage across the battery is the next task. So if you look inside the battery, we have this 12-volt EMF, and then we have this internal resistance, which is 0.2 ohms. The terminal voltage is here. That's going to be 12 volts minus whatever the voltage drop across the internal resistor is, which is just the total current times that internal resistance by Ohm's law. So it's 12 volts minus, we're looking in the real case here, 594 milliamps times 2 ohms will give us 11.88 volts. So that'll be our terminal voltage. If we put a meter across our battery, it'll read a little low. We expect it to be 12 volts, but it'll read 11.88. The more current we draw, the worse that'll get.